So I'm here, I'm Luís Pessoa from INESC Tech in Portugal, and I'm here to present you the TERRAMETA project. So myself, I'm the project coordinator, and the technical manager is George Alexandropoulos from University of Athens. So TERRAMETA in a nutshell. Investigation of groundbreaking technologies towards 6G and feasibility of ultra high data rate communications, leveraging mainly on terahertz meta surfaces or reconfigurable intelligence surfaces, or RIS. How you can choose what you want to call them, but the focus in terms of frequency range, although we call them terahertz, it's mainly 140 and 300. So in some literature it can be called also sub-terahertz, but on another literature is already called terahertz above 100 gigahertz. So we have been focusing specifically on these two frequency ranges, and we have two main goals. So in one hand, on the hardware, so novel high performance hardware, including low power consumption switches, RISs, so reconfigurable intelligent surfaces, and transmitter and receivers for this frequency range. On the other hand, using these design components, so having specifications from the developed hardware to advance on the network analysis and optimization. So as it is very common in these projects, developments are driven by 6G use case scenarios, and in our case, we focus mainly in indoor, outdoor, and indoor to outdoor scenarios, and including a real factory setting and the telecom testing field. So this connects with our end users in the consortium that I'll explain later on. So in terms of objectives, the first one, specifically on the hardware. So this is a very hardware intensive project, and we will develop specifically switches for the RISs, so for the reconfigurability of the antennas, based on memristors and microfluidics, so two different approaches, also following a risk mitigation approach. And so memristors and microfluidics, we will address them as a world first in these frequency bands. We will also address CMOS based switches as a lower risk approach. We will develop transmitters and receivers capable of high power modulation of terahertz signals. So this is a great gap in the state of the art. It's the power levels that you can generate from state of the art devices. And so we will try to modulate directly a high power source from one of our industrial partners. That's also a world first. We will target multifunctional RISs, so either transmissive, so T-RIS, reflective, so R-RIS, and hybrid RIS, so with RISs with sensing capability. Going to the second objective, this is more focused on the network architectures based on realistic models. We will look into the assessment of large active antenna arrays under low power and low resolution hardware, so small number of bits, for example, in the switches. For example, the lowest possibility is to have just 1 bit on and off for the switches, but we will address this kind of cases. The terahertz channel models, and also the network architectures comparing both centralized and cell-free approaches. We will investigate the placement of RISs in the environment to investigate the different degrees of freedom and the sharing of RIS between different nodes as well. On objective 3, the focus is on the signal processing techniques for terahertz communications, focusing mainly on localization and sensing, using the different kinds of RISs that I mentioned. So here, the signal processing algorithms and techniques will consider transceivers and the wireless environment having RISs. And we will also take into account the hardware specifications and the capabilities of the hardware that we develop in the project. This is something that in the state of the art, it's usually a gap. You see a lot of signal processing for this kind of communication systems, but many cases they miss to integrate the actual capabilities of the hardware. And by having this solid competence in terms of hardware in the project, we will be able to make more advanced signal processing that takes into account the real hardware capabilities and limitations. We will also have a dedicated channel sounding activity for the development of channel models. And the focus will be on, as I said, communications, localization, and sensing. So in terms of use cases and demonstrations that we will target, so we have two focus here, one on the telecom side and another one on the industrial edge side. So on the telecom side, it's depicted here on the left. It's what you can expect from having these RISs able to reflect the signal to avoid obstacles. Also the capability of having the telecom signal go across the window from an outdoor to an indoor scenario. So RIS is integrated in Windows, can suit this approach. On the factory edge, factory floor scenario where you have the industrial edge environment, the RIS is installed on this factory will also be able to relay the signal from these assembly robots to the base station or to the control server by avoiding also the occlusions or the obstacles. On a final objective, it's on the active influencing of the standardization and regulation. So like the Times project, in our project, one of the partners, which is actually the same partner, we have one partner that is in common in both projects, and that partner is leading one of the industry specification groups in ETSI, which is the terahertz. And that will put us in a good position to make an impact in there. So we will target to bring to the standardization not only the hardware reconfigurability, but also the channel models and the network architectures. And also influence the preparation of the WRC 2027, where terahertz spectrum is certainly to be on the agenda. In terms of specific focuses of the project, so the development of terahertz RIS technology is of course the main focus, but for that we will need specific materials and electronics technologies that can support this. So as I said, we will target both reflective and transmissive RIS. And the different microelectronic technologies that we target, it's memristors from one side, BCMOS or gallium nitride, and the microfluidics. So we will consider all of these technologies in the development. So this is competencies from different partners of the project. And then on the signal processing, the focus is on the localization, sensing, channel modeling, channel estimation, beam management, baseband processing. In terms of frequency bands, I mentioned briefly at the beginning, so 140 gigahertz band, so the D band, we have around 30 gigahertz of spectrum available for different applications. And in the 300 gigahertz band, and also associated with this IEEE 802.15.3D, that's already on the standard. It's almost 70 gigahertz of bandwidth considered for both fixed and mobile services. Regarding the reflective race design, this one will be the one where we will focus more on these advanced switches, so the memristor, BCMOS, the microfluidic. And on the other hand, for the transmissive race, that we will focus more on the 300 gigahertz band and using a more advanced RF silicon on insulator CMOS process. So that will be also a great challenge, and there has been little development in this in Europe. The state of the art is mainly outside of Europe right now. As finishing the presentation, so this is an overview of the different work packages and how they interconnect. So from use cases to the different technology work packages, and then to the final demonstration and proof of concept. And last slide on the consortium overview. As I said, so INESC is the project coordinator, and the technical coordinator is the University of Athens. And you can have an idea of the different competencies of the different partners and how they interrelate to the delivery of the project. And yeah, and that's it. Thank you for your attention.
Thank you very much, Lewis. Fairly concise presentation and actually slightly ahead of time. Well done. There is one question for you in the Q&A asking what the terahertz power level that you can modulate is. I don't know if you want to answer that now or think about it and either answer it in the chat or answer it later on at the Q&A session. If you give a very short answer.
We'll look into modulating 50 milliwatts.
50 milliwatts. Okay, well, there's a very short answer. Okay, thank you for that, Lewis.